We're going to talk about what's called the squeeze theorem, or some books will call it the sandwich theorem. So in this video, we're going to try to see how this squeeze theorem works so that you can have some kind of exposure to it. That has actually appeared on a recent AP question where you had to know the squeeze theorem. Secondly, we're going to learn, we're going to see a very important limit that we're going to try to find. That is the limit as So we're going to try to show that the limit as x approaches 0 of sine x over x is actually equal to 1. And we'll learn later on what's called L'Hopital's rule, which will be a really easy way to learn and remember this. But until then, this comes up in some kind of surprising places, and so it's going to be one you're just going to have to know and remember. And then after we have shown that, we'll look at some examples of other limits where this ends up working its way in there, and we're going to need to know this limit and remember that limit in order to answer the other limit question. So in the squeeze theorem, what we're going to do is we're going to try to look at 3 different pictures here, and that's going to lead to kind of what we see up here, where the limit we're going to try to show, we're going to kind of pin in between these 2 other limits that we're going to be able to figure out. So by claiming that the limit that we are trying to resolve is in between these other 2, once we take that limit, we're going to show that these 2 that must be either a little bit less, that is less than or equal to our known limit, or greater than or equal to our limit. If we can show these both go to 1, then we're going to squeeze ours, or sandwich our limit in between those, and say then it must be equal to 1 as well. That's the idea behind it. So in our picture here, we can see this triangle right there, and we're going to first try to get an expression for the area of that triangle. We can see from the picture that this triangle, because of that little gap, is going to have to be less than or equal to this sector, and that sector in turn is going to have to be less than or equal to this triangle here that goes a little bit outside. So these limits on the outside are going to be like our h of x and g of x that we see up here, and our limit is going to be stuck in the middle in between those. And then we're going to try to take the limit as x goes to 0, and hopefully we can show that these 2 limits on the outside are going to go to 1, which is then going to squeeze our limit, and we can then conclude that that limit that we're trying to resolve is also going to go to 1. So let's look at the area of this triangle. So we know the area is 1/2 base times height, and the base of our triangle here, because this is a circle of radius 1, then the base of our triangle here is going to be 1. And the height of our triangle is right here. And when we drop that perpendicular in, we can see that we create a right triangle. And once we know the right triangle, we can use our SOHCAHTOA. And we know that the hypotenuse is 1, and that the sine of this angle theta is going to be the opposite, which we've called the height over 1. So that is, we have sine of theta is h over 1. That is, the height is the sine of theta. And so we're going to plug that in for our height. And so we have shown that the area of this first region, that first triangle, is in fact going to be 1/2 sine theta, or our worksheet is going to call that sine theta over 2. Okay, so that's this part that we have done right here. Now we're going to turn our attention to the second one. This is the middle one here. And so again, we have, now this is a sector, so it's not a triangle, but it's a sector. Now in general, the area of a sector is given by, if we were in degrees, we would say whatever that angle is over 360, that would be the fraction of the circle that that sector represents, times the area of the circle, which would be pi r squared. In our case, because we are going to be in radians, instead of calling the fraction of the circle theta over 360, we'll take theta over 2 pi, because 2 pi is going to be that full circle. Then we'll multiply by the pi r squared, but as we've seen, our radius is 1, so that is going to make pi times 1 squared just pi. We can cancel the pi's, and so we can see that this area of that sector is going to be theta over 2, and that's what we see right here. Then moving to that third piece over here, this is another triangle, so the area of this is also going to be 1/2 base times height. Now its base is again going to be this length right here, which is, because that's a circle of radius 1, that's going to be 1. Now the height, which is this distance right here, we can see from our right triangle, we can again use SOHCAHTOA. And so we can use a tangent. We can say that the tangent of that angle theta is the opposite height over the adjacent, which is R1, and so, which is 1. So the height is tangent of theta. And so we can see that that 1/2 tangent theta, we can write as tangent theta over 2, which is what we see right here. So from looking at the pictures and working on the geometry of it, finding the area of those, we can see that this relationship must be true, that the sine theta over 2 is less than or equal to theta over 2, which is less than or equal to tangent of theta over 2. So now we get a clue. We're going to try to multiply through by 2 over sine theta and see what that does to our inequality. So we're going to multiply through everything by that. So we can see on the first one that when we multiply 2 over sine theta times sine theta over 2, that's going to be just 1. We still have less than or equal to. Now when we multiply the 2 over sine theta times theta over 2, we can cancel the 2's and we'll get theta over the sine of theta. And on the last one, when we take that 2 over sine theta times tangent of theta, which remember is sine theta over cosine theta, and to divide by that 2 is to multiply by its reciprocal. And wait a sec, I didn't do that right. So to divide by that 2 is to multiply by the reciprocal of 2. I did that wrong. It should be 1/2 here. So we can see that the sine thetas will cancel, the 2's are going to cancel, and we'll get just 1 over cosine theta. Okay, so far. Now what we want to do, because we're looking to get sine theta over theta, we're going to take the reciprocal of both sides. Now, when we take the reciprocal of both sides of an inequality, we have to change the direction of the inequality. Let's see how that works for a second. We know that 2 is less than 5, but when you take the reciprocal of both sides, 1/2 is bigger than 1/5. So when we take the reciprocal of both sides, the reciprocal of 1 is going to be just 1. We're going to switch the inequality to a greater than or equal to, and we'll go from our theta over sine theta to the sine theta over theta that we wanted, and we're also going to switch the direction of the next inequality, and 1 over cosine theta will become just cosine theta over 1. Now the fun really begins. Now we can take that limit as theta goes to 0. And so when we do that, the 1 is always going to be 1. And we're trying to figure out what's happening to the sine theta over theta. That's our question. And cosine of theta, as we get close to 0, it approaches 1. And so you can see that we're squeezing that sine theta over theta. And so our conclusion then is going to be that the limit as theta goes to 0 of sine theta over theta is in fact equal to 1. Okay, so the process that we did here uses what we call the Squeeze Theorem, or some books will refer to it as the sandwich theorem. So you may hear that. It's the same idea. That idea that if you can pin a limit that we are interested in knowing in between two that we do know that go to the same thing, that's going to force us, that middle, that in-between limit, to go to the same thing. Okay? Now we're also going to remember that. Let's see if we can go to the page here and see how we might use our new knowledge. That is, now we're going to know that the limit as x goes to 0 of sine x over x is equal to 1. So this now is one we're going to have to remember at least for a while until we learn L'Hopital's rule. So let's see what we can do with this. Now we have the limit as x goes to 0 of 1 minus cosine x over x. Let me see if I can make that a little bigger. I think I can. Okay, that'll give us a little more room to work with. Okay, so if we just plug in 0, cosine of 0 is 1, so you get 1 minus, whoops, that didn't do what I wanted it to. Let me try it again. Okay, so if we just plug in the 0, we're going to get 1 minus 1 over 0, and that's 0 over 0, which we know is indeterminate. And indeterminate means we don't know what the limit is going to. We're going to have to do something clever to reveal it. And the clever thing we're going to do is to multiply top and bottom by the conjugate of the numerator. So we're going to multiply top and bottom by 1 plus cosine x, because that will create in the numerator the difference of two squares. So when you multiply 1 minus cosine times 1 plus cosine, you're going to get the a squared minus b squared. That's going to be 1 minus cosine squared in the numerator. I'm going to leave the denominator in factored form and be patient for a moment. Then I'm going to, hopefully the 1 minus cosine squared rings a bell. This was a famous relationship that we talked about last year. If we remember our favorite trig identity, sine squared plus cosine squared equals 1. If we subtract that cosine squared over, we can see that sine squared is 1 minus cosine squared. So we can replace that 1 minus cosine squared by a sine squared x. And now we're looking at this. Now we can split up our limit. So the limit of a product is the product of the limits. So we can think of this. I'm going to take one of those signs and put it over the x. I'm going to take the other sign and put it over the 1 plus cosine x. So these multiply still to get us back. Now we can take our limit as x goes to 0, and we can take each of those limits separately. Now we just said that the limit as x goes to 0 of sine x over x goes to 0. Goes to 1. Oops, I almost goofed that up. Goes to 1. Now we can direct substitute into our second limit, and if we do that, we get the sine of 0, so this is going to be our 1, the sine of 0, which is 0, and then the cosine of 0 is 1, so that's going to be 1 times 0 over 2, which is 1 times 0, which is 0. And so our limit is going to be 0, and we have shown that that is true. Okay, let's try another one. So now we want to take the limit as x goes to 0 of tangent x over x. So again, if we try our direct substitution first, we get the tangent of 0 over 0, but tangent of 0 is 0, and that is indeterminate. So that means we're stuck. So we're going to decompose that tangent. So we're going to say, let's take the limit as x goes to 0, and we'll turn that tangent into a sine x over a cosine x. And then we can say that's going to be the limit as x goes to 0. And this to divide by x is to multiply by its reciprocal. So we're going to move this into this form. And then we can now separate that out a little bit. We're still taking the limit as x goes to 0. I'm going to move that x so that it's underneath the sine and separate out that 1 over cosine x. Now, as x goes to 0, here's that limit that we talked about that's so important that we're remembering is 1. We can direct substitute the 0 for the x there, but the cosine of 0 is 1. And so we're going to get 1 times 1, which is 1. And so our limit as x goes to 0 of tangent x over x is in fact 1. Now the next one is pretty tricky. So as x goes to 0, it's true that sine of x is going to go to 0, and the denominator is going to go to 0, which is indeterminate. So what we need to do is we want what's in this, it's called the argument of sine. So what's in that sine, we need for that to match this. Then as x goes to 0, if these both go to 0 at the same rate, then we can use this fact. So what we need to do is somehow get a 4 into there. So the trick that we will employ as we take the limit as x goes to 0 of sine of 4x over x is we're going to multiply by 1 in the form of 4 over 4. So that is going to become the limit then as x goes to 0. Now I can bring this 4 underneath with that x. So we have sine 4x over 4x. The other 4 I'm going to leave kind of outside there. Now we can see that the limit of a product is going to be the product of the limits. Once these match, now as x goes to 0, these go to 0 at the same rate. So now it's like saying is if we've kind of changed that and called it maybe sine u over u, and we're taking the limit as u goes to 0. So now this limit is going to go to 1, and 4 doesn't have any x's in it at all, so it's just going to stay 4. And so we're going to get our limit as x goes to 0 of the sine of 4x over x is going to equal 4. Okay, that's what we're after. Okay, let's see what we have on the next screen. Okay, and I'm going to see if I can make this a little bigger. Okay, so now what we're going to do up here is take, whoops, didn't go the way I wanted it to there. Let me try that again. So I have my pen on. So up here, we are going to look at these, this limit, and we're going to take it in pieces. So as x goes to 0, the natural log of 0 plus 1 is going to be the natural log of 1, and hopefully we remember the natural log of 1 is 0. Plus, we can do we're just going to take the sum of these limits. As x goes to 0, we can direct substitute in 0. We're going to get 2e to the 0, and since e to the 0 is 1, that's going to be a 2. And then 3 is unaffected by what x does, so that's going to remain a minus 3, and so that limit is negative 1. And the product here, so we've used this in those last examples. The limit of a product is the product of the limits. So in this example over here, I'll go with green. So as x goes to 0, then we direct substitute in 0 for that x, and we've got 3 sine of pi over 2, and that is going to multiply. We direct substitute in the 0 there, and cosine of 0 is 1. Sine of pi over 2 is 1, so we're getting 3 times 1 times 1, so that limit is going to be 3. In here, same thing for a quotient. We're just going to take the quotient of each individual limit. We just have to watch out. We can't let the denominator be 0. If that happens, then different things happen. So we're going to plug in 2 here. So 2 squared is, we're just going to direct substitute in. So 2 squared, I think that is that a squared or a cube? It's hard. I think that's a squared. Is going to be 4, and then minus 3 times 2 is 6, and another minus 2, and that's going to be over 2 plus 2 is 4. So in the numerator, that's going to be a negative 4 over 4, so our limit will be a negative 1. And if we have powers, again, we're going to take the limit of what's inside and then raise it to that power. So that's pretty hard to read on mine. I'm not sure what that power is. I'm going to pause it and look it up and come back. So that is supposed to be, whoops, hold still there. That's supposed to be a 4th power there. So as x goes to pi over 4, we're going to get the sine of pi over 4 and then raise that to the 4th power. So sine of pi over 4 is the square root of 2 over 2. And if we're going to take that to the 4th power, we can square it first. So I'm going to think of squaring this, and then once I get that result, squaring that result. So squaring square root of 2 is going to be the square of the numerator over the denominator, and that's going to be a 1/2 squared. And again, we square numerator and square denominator, and it's going to make that limit be 1/4. Okay, so crazily enough, you can also find the limit of composite functions by first finding the limit of the inside function and then taking the limit of the outside function of that result as we approach that result. So this is supposed to, it's not clear on mine right now, but that's e to the cosine of x as x goes to pi over 2. So first we're going to take the limit as x goes to pi over 2 of cosine of x, that's the inside function, and we can just direct substitute that in, and cosine of pi over 2 is 0. So that then makes us take the limit, it's the limit as x goes to, so it's the limit as x goes to pi over 2 of e to the 0. But e to the 0 is just 1, and so no matter what you get, well, no matter what x does there, that is just going to be 1. All right, very good.